Hi, I'm Martin Sweatman, a scientist at the University of Edinburgh, and in this video I'm going to cover the twists and turns of the ongoing Younger Dryas impact debate. I'll review the research literature starting from 2007 with the seminal paper by Firestone et al. Right through to the present day. And whenever a new paper comes out, I'll review that too. Now, I'm going to lay my hand out right now. I think it's absolutely clear to any reasonable and neutral observer that the impact happened, that it triggered the Younger Dryas mini ice age, and that it was an extinction level event with profound consequences for megafauna and human populations at the time. It's also absolutely clear that this event is memorialized at Göbekli Tepe. It was a major influence on the development of civilization and even our modern day religions with all their catastrophic imagery and baggage. I recommend a video by Ben at Uncharted X on how we still remember this event in our modern religions. So the subject of these videos could hardly be more important for modern philosophers, scientists, and historians. Essentially, we have now discovered the basis for some of the character of our modern civilization, something that modern philosophers should know about. Fundamentally, the question we want to answer in these videos is, can detailed geochemical analysis of the Younger Dryas black mat, which you can see there, which is this band of discolored sediment which is seen across at least 4 continents from North America and now to South Africa, can it tell us what happened nearly 13,000 years ago? Most of the research literature in this area, and certainly the key papers, are focused on this question. Now, the debate in the research papers has been quite hot, sometimes a little bad-tempered, and this is because there is so much at stake. Essentially, our understanding of our place in the solar system, the risks we face, the fundamental basis of much of geology, evolutionary biology, anthropology, archaeology, history, religious studies, and so on. If this impact theory is correct, and I'm pretty sure it is, then we are in for one of the biggest paradigm shifts in science there has ever been. It's a huge issue. And this also helps to explain why some scientists, mainly archaeologists and anthropologists, are so blinkered in their views. Sometimes those closest to the subject are the least able to exercise reasonable scientific judgment. Okay, so enough of the background and the hyperbole. Let's get started. A great resource for this exercise, this review of the research literature, is the website The Cosmic Tusk, which I'll just find for you right now. It's a shameless supporter of the Younger Dryas impact theory, but the reason we're going there now is to find the research bibliography that we're going to review. And this was put together by archaeology student Mark Young. So here is a list of all the papers that he has found that have got some bearing on this Younger Dryas impact debate. As you can see, it's very extensive. Now, I'm not going to take you through every paper in this list in detail because that would be a little bit boring, and actually it's not necessary. What we'll do instead is review this bibliography to point out the key pieces of evidence in the debate and the main arguments for and against the theory based on that evidence. So straight away, we can get rid of entries in this table that arise from conference proceedings like these spring meetings and fall meetings. Okay, it's a delicate point for some people, but here I only want to review primary research papers that have been through a rigorous peer review process. So we're going to leave out anything where the review standards might be slightly questionable. And we'll also skip over any papers that are just opinion pieces that don't actually have any new data or any analysis of new data to offer. So we're going to focus on the evidence only and try to make sense of it without pandering to opinionated commentators. So straight away, this reduces our bibliography to a more manageable list. And so what I've done is I've copied this list into an Excel spreadsheet, eliminated all the articles that are just opinion pieces or are proceedings of conferences, and we're left with a shorter list. Nevertheless, it's still quite a long list with some fairly detailed papers. So what I'll do is I'm going to cover this list in several sections. And in this first video, I'll tell the story of the first couple of years from 2007 with the original paper by Firestone et al. Right through to the end of 2009. Okay, so let's get started. First, I'm going to show you the data that supports the impact theory in these first few years, 2007 to 2009. And this really helps to set the scene. And then I'll show you how opponents of the theory reacted and the data they brought to the discussion, and how to make a balanced scientific judgment about this first salvo of research papers. And by eliminating the dross, we've reduced the first 60 entries in this table to a much smaller list. So that's what I'm going to review in this video. So let's start with the original 2007 paper by Firestone et al. Let's take a look at the abstract. Now you can pause the video here to read what it says in detail. Basically what they're claiming here is that a major impact occurred nearly 13,000 years ago that altered Earth's climate. It triggered changes in human cultures in North America, and it caused an extinction, or it caused the extinction of many species of megafauna, at least in North America. Now it's important to be clear, they are not claiming in this paper that the impact instantaneously wiped out all these people and animals, or immediately triggered a plunge in Northern Hemisphere climate of around 15 degrees Celsius. What they are claiming, though, is that this impact is the primary trigger for these later events that might have unfolded over dozens or even hundreds of years. So let's look at their key data. So they analysed the sediment at the bottom of the black mat in several locations across North America. Okay, here it is. And they were looking for a range of indicators that point towards a cosmic impact of some kind. So these are all their plots of different sites for different kinds of indicator. I'll just enlarge it slightly again. Okay. So you can see they were looking at things like charcoal, glassy carbon, carbon spherules, magnetic grains, iridium, and so on. And these are all plots of measurements of whatever substance they're looking at, plots with depth through the Younger Dryas black mat, which you can see as this sort of horizontal band in the photos. Now it's absolutely clear from all of these plots that they have found some very interesting signals that are hard to explain except in terms of a cosmic impact. So they find spikes in carbon, magnetic spherules, other spherules, magnetic particles, iridium, both in the sediment and inside the particles, something they call exotic helium and fullerenes, glassy carbon and other unusual elements like nickel and chromium. And they show that these signals are in each case centered near the base of the black mat. Now you have to go to the supporting information to find a map. Let's just do that. Go to the supporting information to find a map of where these sites are. Okay, here we go. So you can see that they are clustered over on the east coast, and there are a few in present-day Canada, one near the Great Lakes, and a few in the south. I think this map would have been better included in the main paper. Anyway, that's not an issue. Go back to their data. Let's see, here it is. We can see that the largest signals come from Gainey, this site in Gainey, the magnetic grains. We have nearly 4 grams per kilogram of magnetic grains, and likewise. So this is perhaps the highest signal of all, and that location is here near the Great Lakes. So it seems that if something happened, whatever event happened, it was towards the north of North America, perhaps near the Great Lakes and other places. The debris that resulted from the fallout of this event is is not as much as it is at Gainey. So what should we make of this evidence? At first sight, it appears conclusive. Something dramatic clearly did happen 13,000 years ago. You can see the ages here. At the base of the Younger Dryas black mat are closely clustered around the onset of the Younger Dryas event. And let's just go again to the supporting information. So the onset of the Younger Dryas event is around 12,900 years ago, which is what they find, which corresponds to the level in this the black mat that they find. Okay, so what should we make of this evidence? At first sight, it appears conclusive. Something dramatic clearly did happen 13,000 years ago, unless they're manufacturing the data, which is an unreasonable assumption at this stage. They find consistent signals for a wide range of indicators and at a wide range of sites. And it's obvious this data cannot simply explain by random chance. The correlations are too strong. So the data appears to be real. But it's not at all clear from this data whether this event had anything to do with the Younger Dryas climate event or any megafaunal extinctions or human cultural changes. This data is purely geochemical analysis. All we can take from this is that very likely some kind of large cosmic event occurred. Now, the next paper by this group supports this with additional nanodiamond evidence. So I shall find that paper. Here we go. It's quite a short paper, just a single page, but it's in a prestigious journal, Science. And so they find, well, they claim to find nanodiamonds in the Younger Dryas boundary layer. So at the same location as all the other signals, they find nanodiamonds, and they confirm that by performing these electron scattering experiments. So we can add nanodiamonds to the list of signals, which is important because they're a very strong indicator of some kind of cosmic impact. And then in their next paper, they provide even more evidence of the nanodiamonds by finding evidence for a specific kind of nanodiamond or structure of nanodiamond known as Lonsdaleite, which can only form under highly exotic conditions of high pressure, high temperature, like a massively hot explosion. So it seems very clear, there can be no real argument about this. It's practically impossible to get all this data by mistake or to manufacture it to make it up. So the only question is, what exactly did happen 13,000 years ago? What kind of cosmic event was it? And what effects did it have? So clearly it was dramatic and highly unusual, and almost certainly some kind of rare cosmic event. But let's see how their opponents react. Remember, there's a lot at stake here, much of our understanding of several major areas of science. A lot of scientists will need to radically change their views of the past to accept this new idea, this impact idea. So we should expect some kind of quite irrational responses from some of the experts in the field. So let's see what one of the most eminent anthropologists in America, who's expert in this area, has to say. This is Vance Hayes. He's an emeritus professor, which means that he's been studying this field for a very long time. He's very experienced, and he's actually worked at one of the sites analysed in the original paper, Murray Springs, for much of his life. So he knows that site extremely well. So let's just see what he had to say. Actually, he does us a favour. He points out the relevance of this Younger Dryas black mat to the debate on the megafaunal extinctions and the human cultural changes. So you can read his abstract. Again, if you pause the video here, you can read his abstract carefully. But what he's confirming is that something dramatic and sudden and practically instantaneous happened nearly 13,000 years ago. He states that the black mat is like a marker in time that separates the world from before the event from the world after. Before, there were many more species of megafauna, and the what's known as the Clovis human population in North America. And after the event, or after the black mat occurs, many species of megafauna become extinct, and there is a significant change in the human culture in terms of their technology, spear points, and so on. So essentially the people after are either a new population who replaced the older preceding Clovis culture, or the Clovis culture had to radically adapt to new conditions. Okay, but although it's clear to him, if you read the rest of the paper, it's clear to him that something dramatic happened, he's not keen on the cosmic impact scenario. And you might expect him to be just a little bit skeptical, because the evidence has been under his nose for decades. He's worked at one of these sites, Murray Springs, and he's missed this data. But he can't just dismiss the geochemical evidence because it's so compelling, but he is skeptical. And there's a nice paragraph later in his paper which reinforces that view. So if you read this next paragraph here, again, it just reinforces what he was saying in the abstract, that this is a very dramatic and sudden event with consequences for megafauna and human populations. Now, his paper doesn't provide any evidence for or against the impact hypothesis, but it does show how uniform the event is across America with this plot. So this is essentially a stratigraphical record at lots of different sites, some of the ones that were analyzed by Firestone et al. A stratigraphical record of essentially the black mat across different parts of North America. And so you can see how, in his view, the black mat lines up temporally, in other words, at the same time across all these different sites, and how it separates the world from before the event from the world after. So as he says, the black mat, or the base of the black mat, can be viewed as a marker in time that occurs at the beginning of the Younger Dryas period. And that's the view of one of the most senior scientists working in this area. But our next paper is much less enthusiastic about this impact idea. In fact, these researchers not only reject the geochemical evidence of the Comet Research Group, but they don't provide any alternative reason for its existence, they just essentially ignore it. But they also reject the generally accepted view held by Vance Haynes and others of there being any cultural changes in North America at this time. So what these guys do, this is their main plot, what all their discussion is about. So what they do is they compile all the radiocarbon evidence from many archaeological digs across North America from around the time of the Younger Dryas impact, and then they lump them all together to create a view of how human population changed at this time. Now, if there was actually a bottleneck in human population at this time, separating the Clovis culture from before, from the various Paleo-Indian cultures that came after, you would expect to see a dip in this plot at the time of the Younger Dryas impact, which is here. And although there is a dip, it's not very large, and there are other dips in this plot that are just as large that suggest there is nothing particularly special about or unusual about this dip that happens at the time of the Younger Dryas event. So at first sight, this seems like a blow not just for the impact hypothesis, but a blow for many scientists, including Vance Haynes and others working on this issue, who thought that the black mat was a geosynchronous marker of extreme changes across North America. These guys are saying that there was nothing special that happened at this time, at least nothing special that particularly impacted human populations. So who are we to believe? How can we reconcile this data with what we've already seen? They look to be completely contradictory. Now, to make sense of this new data, it's important to understand the concept of uncertainty in measurements. Now, this is a fundamental issue in all science, and something we teach our undergraduates in their first laboratory sessions. My feeling is that this fundamental issue is not something that is so well taught in other disciplines like archaeology, where in recent decades less scientific practices have become popular. Nevertheless, as a scientist, whenever I see some data that doesn't seem to make sense, or it looks dodgy, one of the first things I do is to check the uncertainty in the measurements. And very often this is where the problem is to be found. Anyway, key point is that to be useful, any measurement must be accompanied by an error estimate, okay, which is like an estimate of the uncertainty in the measurement. And you might have heard of things like error bars or the standard error. It's all the same thing. So suppose an archaeologist makes a radiocarbon measurement of the age of some bones, let's say. And suppose they get a result which says the age is 15,000 BC plus or minus 500 years with 95% confidence. What this means is that if the measurement on the same sample was to be repeated many times, 19 times out of 20, an age between 14,500 and 15,500 BC will probably be obtained. But one time in 20, we can expect the age to be slightly outside this range. Now you might think this uncertainty means that we can't ever know anything about anything with absolute certainty. And you'd be right. That's the whole point of science. Science is about confidence, not certainty. It's about finding the most likely explanation for observations, not some unattainable view of the truth. Good thing about science, though, is that for many things, our confidence is so high that we can just assume they are true and not worry too much about it anymore. Now, specifically considering radiocarbon measurements, there will be different uncertainty ranges for every different radiocarbon measurement. Sometimes it can be very large, say thousands of years. Sometimes it can be very small, say just 10 years or so. Now it happens that the radiocarbon measurements, any radiocarbon measurement of any object from around the time of the Younger Dryas period, they will all naturally have quite a large uncertainty. And this is unavoidable, and it occurs because of the way radiocarbon ages are calibrated. And essentially, this problem is hinting that a great upheaval in the environment took place at this time. And it makes estimating radiocarbon ages of materials from this time more difficult or more uncertain. It follows then that any radiocarbon measurements from the Younger Dryas impact period must be handled with caution because the uncertainty in the measurements, or the error bars, are usually quite large exactly at this time. Okay, so now we can understand what has gone wrong with this paper. Essentially, it's because of poor data selection for two fundamental reasons. First, if we are looking to observe a dip in human populations on the time scale of, say, a few hundred years, which is thought to be the case here with the Younger Dryas impact, we should only consider data, radiocarbon age data, with an uncertainty less than this level, less than a few hundred years. So data with an uncertainty much larger than a few hundred years is just going to smear out the result. It will hide the true response of the system. Now, Buchanan et al., people who wrote this paper, didn't do this. They used all the radiocarbon data regardless of its uncertainty level. And for some of the data, this was thousands of years. Their second mistake was to not look at the context of their data. They basically ignored whether the radiocarbon measurement of an object, or whether the radiocarbon measurement was made on an object from above or below the black mat. And remember, the common consensus is that the black mat marks an instant in time which is synchronous or consistent across North America. So to ignore this fact is to ignore an important piece of information. Essentially, Buchanan et al. Are putting much more confidence in the radiocarbon measurement, even though they're quite uncertain, perhaps by thousands of years. They're putting more confidence in that dating than whether the object is found above or below the black mat, and therefore before or after the Younger Dryas event, whatever it was that happened. Well, that's just crazy. It's a flawed methodology. Basically, if you wanted to obfuscate investigation of the Younger Dryas event, you would do exactly what Buchanan et al. Did in this paper. It would be a very good way to obscure the evidence or obscure the truth. Their study, it would have been fine if they had used much better control over their data selection. But as it is, they didn't, and so it's a shoddy piece of work. In any case, their paper says nothing about the geochemical evidence. It's simply concerned with the human population response to whatever took place. Now, the Comet Research Group pointed this out to Buchanan et al. In their response papers, but Buchanan et al. Did not address these concerns because they couldn't. They discussed other things in their response, but not the central and fundamental concern of data selection. So essentially what I suggest is that we ignore their paper and the responses to it because it's a flawed piece of work. So we can just delete them from our list. So let's just do that. Okay. Let's move on. The next couple of papers are not so easy to dismiss, these two papers here. In 2009, opponents of the Younger Dryas impact theory published two papers that did some serious damage to the theory. Now, 4 of the authors are common to both of these papers. Let's see who they are. They are the common authors are Surrevell, Todd Surrevell, Vance Holliday, Vance Haynes, and Philip Clays. Let's just find the other paper as well. Here we go. Todd Surrevell, Vance Holliday, Vance Haynes, and Philip Clays. Okay, so these are 2 papers from more or less or very similar research groups. Now, each of these authors, they are senior archaeologists, anthropologists, or geologists in their disciplines, and they all are expert in this period, the Younger Dryas period in North America. So let's see what they found in their papers. So in this first paper, where Surrevell is the first author, these researchers tried to reproduce the findings of the Comet Research Group for the abundant spikes in magnetic grains and magnetic spherules at the Younger Dryas boundary. Okay, but they're only looking at the magnetic grains and magnetic spherules and nothing else. None of the other signals are analyzed in this paper. And they looked at a range of sites, 3 of them the same as the Comet Research Group. So Blackwater Draw, Lubbock Lake, and Topper are the same, and the other sites are different. Now, the Lubbock Lake site is interesting, or the data is interesting, because here they do confirm peak at the beginning of the Younger Dryas boundary in magnetic grains. But they also find a peak in magnetic grains at the end of the Younger Dryas period, when the climate suddenly improved again. So that's like a positive result for Lubbock Lake for magnetic grains, but for the other sites, none of the other sites have similar kinds of correlations or patterns, including the sites that the Comet Research Group looked at previously, so Topper and Blackwater Draw. They don't find peaks in magnetic grains at the base of the Younger Dryas black mat. Nothing seems to be obvious. In fact, the data for the magnetic spherules is even worse. The data for that is very patchy and inconsistent. So that also, it looks to be completely random, with no obvious correlation to the bottom of the black mat. In fact, these authors make a good point about the magnetic spheral measurements. How do you define a sphere? And this is what they ask. How can you count the number of spherules in a sample if you don't have a good definition of when a particle is spherical enough to count? That's essentially what is a sphere. So they effectively eliminate the spheral evidence of being as much use, as they are too hard to define properly. So that means that we should focus on the magnetic grains. So that is that first paper, where essentially they are unable to reproduce the data of the Comet Research Group for magnetic grains. Let's have a look at their other paper. So in this paper, first author is Paquet. They are looking for peaks, abundance peaks in the rare elements like iridium, ruthenium, platinum, palladium, and so on. Now remember, the Comet Research Group found raised levels of iridium at the base of the Younger Dryas black mat. That's these symbols here, these black and white symbols here. Okay, so here we have on this scale the magnitude of the measurement, and here along the bottom the different elements that have been measured at the base of the black mat. So what these authors find again, according to their measurements, is that there is no particularly suspicious or raised level of these rare elements at the base of the black mat. Okay, so their data are these lines which more or less follow the line, this red line here, which is what you would expect to find in the Earth's crust. So that they don't find anything unexpected at the base of the black mat, completely contrasting with the Comet Research Group results for iridium, which are similar to abundances of iridium that we find in other impact sites like the Chicxulub crater. Well, this is odd, and if we look at the magnitude of the difference here for iridium, okay, the measurements made by the Comet Research Group are many orders, in other words, many powers of 10, hundreds, thousands of times higher for iridium than measured by in this new work. So this is really odd. If the impact theory is true, we would expect the geochemical data indicating this impact would be reproducible, but apparently it's not. These two data sets are completely inconsistent, except for the magnetic grains at Lubbock Lake. So what's gone wrong? How can we reconcile this data? Logically, there are only two explanations for these differences. Either one group is telling porkies and basically manufacturing the data, like lying, or one of the groups has used the wrong method to sample and analyze the soils. Now, I don't normally like to accuse people of lying without good evidence, so the most likely explanation is that one group has used the wrong methods to create the data. Now, the question is, which group is right and which group is wrong? Now, at this point, it's worth remembering that this kind of analysis is not easy, and although the methods should be described well enough by one group so that the other group can follow the same procedure, it's not often quite the case. It's never that simple. So errors in sample preparation, soil sample preparation and analysis are entirely possible and quite likely. And also remember, nanodiamonds have also been found at the base of the Younger Dryas black mat. And these are another very good indicator of some kind of cosmic event or a cosmic impact. So at this stage, the most likely explanation is it's the opponents of the impact theory, who are all proponents of pre-existing alternative theories for the demise of the megafauna and changes in human population, like climate change or overhunting. Probably it's the opponents of the impact theory who have made some errors in their analysis of the samples. But we can't be sure of this. Okay, we can't be sure. So how can we decide? Basically, what's needed at this point is for a third group to enter the debate, who are experts at this kind of soil analysis, to see if they can reproduce the data suggesting a cosmic impact. And this third group should be independent, so unconnected to either the Comet Research Group or their opponents, so that they've got no skin in the game. But at this stage, this data, which has been unable to reproduce the data of the Comet Research Group, the impact theory is in quite a lot of trouble. So we'll see in the next video what happened next. Okay, well, thank you for watching. If you like that, stay tuned for more. You can read my book, Prehistory Decoded, and you can also have a look at my blog, martinsweatman.blogspot.com, for other articles in this area. So we'll continue this discussion in the next video in about a week's time.